So I think this is a quite amazing argument because the argument is really simple. And if you try to think about that, it is trying to say that because the system prefers to have more domain walls, the statistical weighting for those spin configurations with more domain walls actually will be larger. And because of that, the system's statistical behavior should be a disordered configuration with many domain walls. And that usually suggests that the finite temperature will introduce a quantum fluctuation in one dimension that is so strong that it will actually kill the possibility that the system could have some ordered pattern. So the important thing is about the argument actually works for any temperature that's non-zero. So that also suggests that when we are trying to understand or try to guess this phase diagram, we should anticipate no order the phase at any finite temperature region. And even though we use our arguments for the all spin pointing up state or all spins point up configurations, if you run the similar arguments, you'll find the argument also works for all the spin down configurations. So at this moment, are there any questions? Okay, so I think that's a simple argument but full of physics. So if you did not absorb that right away, please try to think about that afterwards. Okay, so now we can try to look at these arguments and identify the key step is actually comparing the configurations with no domain walls and the configuration with one domain wall, and ask what is the free energy density, what is the free energy difference between these two systems. And we realize that at the thermodynamic limit, entropy can easily overcome the energetic effect in this simple one-dimensional system. So at this moment, we can ask ourselves what happened if we try to go to a two-dimensional system. Okay, so let's try to discuss that. So we can try to ask what is the corresponding analogy in 2D. So okay, good. So we still have this phase diagram. And for 2D, the t equal to 0 phase diagram is still the same because the t equal to 0 phase diagram is not sensitive to dimension. So what we are trying to ask is what happened here. Is it going to be similar with the 1D case? So similarly, we start from the phase with the spin configurations that are pointing upwards. But what does that mean in 2D? It means that all the spins are arranged on a square lattice. Okay, so let me try to draw a minimum set of them. Yeah, and of course there are more other spins nearby. So just let's try to focus on this patch of the spin configuration. Okay, so this is the no domain wall configuration. So what we want to calculate is or estimate is the free energy with no domain wall. So let's try to just label it by F naught, and we'll do the calculation a little bit later. So immediately we can realize what is the simplest way to create a domain wall is simply I just flip one spin right here. Okay, so once I flip that spin, the energy will be changed for the nearest neighbor bonds, and there are 4 nearest neighbor bonds. And as in 1D case, because the energy is changed, this configuration actually will have a higher energy compared with the previous case. So once we have it, we create a domain wall that basically surround this flipped spin. So with this idea, we immediately notice one thing, that if I try to flip multiple spins, actually I could have a domain wall with different pattern of the domain wall. So if we try to denote the circumference of the domain wall by n, then in principle this length n loop can have various different kind of shape. I don't know, it can be any shape. So those different shape will give us the same energy, but they will have some non-trivial entropic effect. So instead of counting the calculating the free energy for like the number of domain wall, instead we should focus on the free energy of a domain wall with circumference n. And what we want to calculate is the difference between these two free energy, and then we want to ask whether the system prefer to have this domain wall or not. So as previously we just did in the 1D case, we know that once we flip the spin, we will create a anti-parallel the spin configuration, which calls us energy minus 2j. And because the circumference of this domain is n, so the energy cost to create that domain wall is basically minus 2j times n. And then what we still need to do is we need to ask what are the possible entropic effect for this domain with circumference n. So we want to, oops, this is not this. This is the entropy. And this capital N sub n is the number of possible closed. So how to estimate this N. One simple way is that you just start from some bound, and then you can ask, once I create this anti-parallel configuration, I can ask like okay, so let me try to draw it in this way. Suppose we start by choosing this green bound to be the anti-parallel configuration. Then that means that we determine the this little purple segment of our domain wall. Then the next question we can always ask is that how to extend our domain wall. So at this point, basically we have three choices, 1, 2, 3. And in this particular configuration, we choose to extend the domain wall on the direction 3 with one segment. And that means here we create a anti-parallel nearest neighbor spin configuration, which costs us some energy. So now we face our second choice. We can ask how we are going to extend the domain wall. We can go again upwards, or to the right, or bend below. So in this particular configuration, again, we choose to go to a right and introduce the anti-parallel spin configuration correspondingly. So you can see immediately that we made our choice at this point, which has three possible choices, and then we made our second choice at the at this point, and again we have three possible choices. So it is very tempting to estimate the number of configurations for a domain wall with length scale n to be z minus 1 to the power of n. And here z is the coordinate number, which in d-dimensional hypercubic lattice, this z is simply 2d, because you can always move forward or backwards in all the possible d dimensions. So that's why z equals to 2d. And in this really two-dimensional system, this 2d is equal to 4, and 4 minus 1 is 3. So that's why every time we have a choice, like three different choices to extend the domain wall. So this is just a very rough estimation, but this estimation has a problem, because after n step, it is not guaranteed that you will get back to your original position. So it means that the pattern you formed might not be a closed loop. So the true configuration for the closed loop will be smaller than this simple-minded counting. But let's try to use this simple-minded counting, which has more which overcount the possible configuration, which means that it overemphasizes the effect of entropy. But let's try to put that in and see what is the influence of the free energy difference. Okay, so let me try to copy that. Okay, so here we are going to estimate the free energy difference between the configuration with no domain and the configuration with a domain wall with length n. So this is going to be the approximation, and also, as I mentioned, this contribution of the possible configuration is overestimated, so entropy effect is overestimated. Okay, so even when the entropy effect is overestimated, you can see there's a scale related to the circumferences. So if I pull it out, it will become oops, I think there's a temperature T I missed here. Okay. So what does that mean? It means that for a system with a domain wall with circumferences n, we can always find a temperature such that it is small enough that the entropy effect will be suppressed and the energy effect will win. So when T is smaller than Tc, which is wait a second. When T is small enough such that it is smaller than this critical temperature Tc, then actually the system does not like to have domain wall. And if the system does not like to have domain wall, it means the system prefer to form a ordered state. I think I will stop here because it is a good time to think about the two difference. And again, I realized that I run over time for 10 minutes. So let's take a 20 minutes. Let's take a 10 minutes break, and then we will continue at 3:30. And if you have questions, please let me know.
林老师，
嘿，请问，
就是上面的那个 phase diagram 呢、
嘿，
如果我今天是在磁场等于零的情况下，那我是在绿色区域还是在红色的区域？
非常好的问题。这个我等一下会讲，但是基本上你没办法决定，就是其实我们刚刚讲的已经差不多讲了一件事，就是你的问的题是刚刚好在这条线上发生什么事。然后我们刚刚的这个 argument 是说，如果我的起始状态是像这样子，就是起始状态可能是绿色的区域，或者是桃红色的区域，那这个 phase 会是某种程度上robust against thermal fluctuation， 所以你的 phase diagram 会看起来比较像是这样。OK， 然后接下来你要问的问题是，
它一定是弧形
啊？
就那个区域为什么一定是弧形？
哦，没有一定是弧形，只是其实你可以 argue 它为什么是弧形啦，原因是因为你的温度越高的时候，意思就是能量越不重要，所以你就越喜欢有就是更多的 fluctuation。当你有更多的 fluctuation 的时候，你的 spin 就是 up down up down 会更分布的更均匀，所以某种程度上你的magnetization 应该要是被suppressed 的。对，就是你的自旋会比较不会喜欢某一个方向，它会就比方说你一开始的时候在最 t 等于0的时候是真的 m 等于1嘛，在这里是真的 m 等于1 ，OK。但是如果你开始有 finite temperature 的时候，你就会想象这个 m 应该是要越来越小，所以所以我们会 expect 就是当你开始有 finite temperature 的时候，你的这个 region 应该是要慢慢的变小一点 ，compared to 你是就是在零温的时候。不过这个 argument 从这边看可能有点怪啦，其实它不一定真的要是这个样子。等一下我会画一个三维的图，可能会比较清楚，就是因为我们想要问的是 magnetization 嘛，所以其实你可以问一个这样子的情况的问题。所以它好吧，我觉得我不应该说它是圆弧形，因为圆弧形应该是画 magnetization 的时候它会是圆弧形，就是如果是 magnetization 它是真的是这样。但是如果是画磁场的话 ，B field 应该是要在就是第三个轴，那它应该是整片都是那样，不是只是圆弧形，对吧？不过 anyway， 等一下我会再修正这个讲法，因为这里还没有讲到。不过你一开始的问题不是这个，你一开始的问题是，你一开始的问题是这一段是发生什么事情？就是假设 OK， 我们现在告诉你说，这个所有自旋向上的 phase， 它会至少在有限温度的时候，它还是会活下来，所以我们会知道它会 extend 到一个 region， 那不一定是圆弧形，但它会 extend 到一个 region。那中间发生什么事？那 it turns out 是它只能选边站，就是当你从假设你在磁场等于0，然后你是从比较高温往下，我找另外颜色好了，这个用什么颜色啊？绿色好了。假设你是从高温往下，你就是往这里走，那你就会发生的事情是，高温的时候就是乱的嘛，就是大家都乱七八糟的 paramagnetic phase。但是你撞到某一个就是 critical temperature 的时候，你就必须要选边站，就是你要喜欢，你会变成所有自旋都上，或者是所有自旋都是下的组态，然后这个行为就叫做 spontaneous symmetry breaking。那等一下我会讲更多一点，就是什么叫选边站，就是你从这边下去的时候，糟糕，你从这边下去的时候，会 depends on 你的系统的一些 detail， 比方说 initial condition 然后干嘛的，那你就会选择你会比较往自旋向上或自旋向下，即使你的 Hamiltonian 没有破坏这个对称性，然后这个事件要发生，基本上也是和你的 thermodynamic limit 非常的有高度相关，因为你必须要有 thermodynamic limit，你才可能让这件事变成一个，又可以让选边站变成一个没有模糊空间的事情。因为如果你是有限系统，你总是有一定的 probability，finite probability，你可以从所有的 spin down 变 spin up，可能几率很小，但是它一定是有限的。但是当你是 thermodynamic limit 的时候，这件事就可以被指数型的 suppress， 所以说它就不会发生，所以就只能选边站。大概是这样。 所以会发生的事情就是它会选边站。
那我再问一个问题，就是你刚刚在画那个 domain word 的时候啊，你旁边你有写说那个number of possible closed domain word，为什么你要特别强调 close？
因为这个系统你一定要是 close 的，因为不可能有不 close 的，因为你的 background 都是上嘛。你翻一个下的话，它的 domain word 长这样。但你翻2个，它就变这样，它永远都是关起来的。就如果是一个统计力学上合理的 domain word，它一定要是关起来，因为你不可能有开的。那原因是什么？如果你有开的，那它会变成很奇怪，它会变这样子。假设这样好了。那抱歉，假设这样子。那你从 domain word 你就知道，这里有一个 domain word， 意思是这个 spin 一定跟这个 spin 是相反，所以我就可以画它是往下。然后这里有一个 domain word， 我一定也知道这里和这里是相反的，所以这里有另外一个 spin。但是如果我知道这2个 spin configuration， 我这里不可能没有办法知道，我一定是有办法知道，因为 background 是 spin up 嘛，所以说这里的 spin 也是 spin up。那既然这个 spin 跟它相反，那这个 spin 也一定会跟这个相反，所以这里一定也有 domain word， 然后这里也一定会有 domain word。所以说你的 domain word 会是关起来的，它不会是 open 的。所以我们现在这个估计其实是一个很粗糙的估计，那它会导致你的 loop 有可能就是你走一走以后它不会关回来。那这个当然不是一个合理的 domain word configuration， 但是我们现在还是把它算进去，原因是因为这样比较好算。那如果你把它算进去，你也知道一件事情是你这样子数太多的组态了，所以说你 overestimate 你的 entropy。所以说这里得到的结论其实是一个在你 overestimate 你 entropy 以后的行为。可是这告诉你一件事，即使在你 overestimate 你的 entropy 的情况下，你还是可以发现你的 order phase 是有可能存活的。所以说它是更强的 argument， 也就是说你的 entropy 其实应该要比这个小，就 entropy 其实对于摧毁这个 order 的能力其实应该是更弱的。但是即使在你让它因为计算上的方便让它变得摧毁的能力更强，你都还可以有一个正常的 order 活下来，那就告诉你说这个 phase， 这个橘红色桃红色和绿色的这个 phase， 它们其实应该是有办法 robust survive to some temperature 的。对，所以大概的概念是这样。
然后你这边只有 spin up 就只有往上跟往下的 spin 也是比较暴力的把它粗分为这2种，因为如果有45度角的话，或者让其他转其他角度的话，
这是一个好问题现在的情况是因为我们在考虑最简单的情况，就是 Ising。那 Ising 它的 degree of freedom 是只有2个，就 binary 的，它只能 spin up 或 spin down。那你会说这个一点都不 physical， 因为在材料里面，我们的小磁铁们他们是各种方向都有可能，为什么它只是 spin up spin down？ 那事实上就是这是一个数学模型，就是它没有保证说它一定要 always work。但是，一旦你说可是你还是可以问下一个问题。好，那我们现在知道这个数学模型它会有这个行为。如果今天我考虑我的自旋是可以旋转的，就像你讲，它搞不好有45度的情况，那会发生什么事？那 it turns out 会发生的事情就是你的 entropy 的组态会更多，因为你的 domain word 不再只是用这种简单的方法定义，因为45度的时候，你可能就会有比较麻烦的事情，是你的 domain word 的 energy 会 depends on 你的角度是多少。因为通常你会有角度的行为，你可能就变成你的 Hamiltonian 不再是我们在哪里啊？我们 Hamiltonian 现在是这个很简单的写法嘛。如果今天你是有45度这种概念，表示你的spin 应该是某种 vector。 那这种如果它是某种 vector 的话，那它一定是要是某种内积之类的东西。那你的 n 这里就会必须要有某些 angle 的角度的关联性。那你的 energy 的 estimation 就会是一个和 angle 有关的东西，而且这个 angle 会和你的第几个第 i 个和第 i 加一个的 angle 有关，然后你要 sum over 所有的 i 这样。那这个就会变成一个比较复杂的 estimation。那现在我们只是用最简单的模型，就是用 Ising model 去 argue 这件事，就是我们会有 phase transition， 然后我们也想要知道你刚刚问的问题，那这为什么这里它会开始选边站？然后当我们知道一些这些 discrete version 的 Ising model 会有什么行为以后，我们可以再去问，当它是 continuous 的时候会发生什么事？就是如果它可以continuous 旋转的时候会发生什么事？那 it turns out 是，如果你的系统可以就是自由度可以 continuous 旋转，它 entropy 会更大，那它就即使在二维，这个 fluctuation 都有可能就是杀掉你的 order， 所以你在二维可能也不会有 phase transition in a conventional sense。但这个就是还要再更细节的讨论，就是我们现在还没有到那边这样。OK，
好，谢谢老师。
哦，不会。All right, so hi everyone, welcome back. I think there are several good questions during the break, so I will just rephrase that in English. The first thing is that what we are discussing is the region with, to some extent, have a very well-defined background where all the spins are pointing in one direction, and we ask what is the effect of domain wall to this background order. And we said that even though domain wall can give us some contribution about the entropy, and through our argument, even though we overestimate the effect of entropy, the entropy is still not strong enough to break the order. So we said the order will be robust. But that corresponds to the fact that we believe that this pink region can be extended to some finite temperature region. Okay? But that also suggests that correspondingly the green region can be extended to some finite temperature region. But that's the case when we have a well-defined configuration where all the spins are pointing upward or downward. And the question during the break is, what happens if we are at the point where there's no magnetic field? What will the system do? And it turns out this is something that we are going to discuss. It turns out if you try to go from high temperature along this no magnetic field parameter region, and you try to lower your temperature from the high temperature region to the lower one, at some point you will be forced to make a choice such that the system can only choose to have all the spins pointing upwards or all the spins pointing downwards, or more or less like this kind of concept. It's not like exactly, but because at finite temperature we still have some fluctuation, but you will see what do I mean by that a little bit later. But the point is, at this special critical temperature, the system decides to break its symmetry statistically, because when we choose the parameter region where there's no magnetic field, basically our Ising model has a very nice V2 symmetry. Where's our Ising model? Here. When magnetic field is zero, this Hamiltonian basically is invariant when you flip all the spins at the same time. So when we lower the temperature, the system is saying that even though the Hamiltonian have that symmetry, but as a system, I decide to spontaneously break that. So that actually is a quite mysterious behavior, why the system is doing things like that. And that is one of the phenomena I think I must say, because this notion is so important that it applies to the statistical mechanical system, but also plays a crucial role in the study of particle physics, like and also superconductor. So so we are using the simplest example of Ising model to demonstrate this point. So you will see a bit later how the magic happened. Okay, so that's the first thing. And the second thing is about how about the case that maybe the spins can orient itself in some kind of 45 degrees instead of spin up or spin down. I think that's another good question. And the fact that we only consider spin up and spin down is because we are trying to focus on the simplest mathematical model where the spins are just binary variables. So whenever you want to put in the idea that the degrees of freedom sitting on side x actually can have some angle or some direction dependence, that usually means that this little spin is some kind of vector. And if you have two vectors and you want to form the corresponding energy, that usually means that you need to get a scalar. So the simplest way is you just form some kind of inner product of your system. And suppose we still have some coupling J in the front, and we want to consider this as our new Hamiltonian. Then we can ask, if we do that, can we ask similar question whether we have phase transition or not? And it turns out that the physical intuition is that once you have this little spins acting like some kind of vector, that usually means it is required you to have the inner product to form a singlet under the transformation. And usually it also means that this inner product will contain some information about the angle between the spin on side x and the spin on side x plus 1. So that means that the energy difference will be a bit more difficult to calculate when you try to calculate the spins on the domain walls. So because now these spins could have different kind of angle pattern on the circumferences. So that means you need to do a more complicated calculation to estimate your energy. So that's the first difference if you try to start think about the spins as some kind of little vector instead of the binary variable. However, the more challenging part is actually once you allows your spins to pointing in different direction, it also means that the entropic effect will be stronger, because previously the binary variable only have two choices. Now if you allow your spin to point in any direction, that means basically a larger degrees of freedom for this system to behave. So the entropic effect will be enhanced. So what does that mean? It means that maybe the conclusion that we got that the order will actually be robust against finite temperature fluctuation might not be true. And we need to think about what happened. So it turns out that this intuition is quite correct, because the simplest generalization for the Ising model is what we call the XY model. The name is called XY model because now we allow the little spins to point in two-dimensional plane, basically the XY plane, and it is characterized by this little angle theta. And you can try to play the mathematical calculation, and you will see if you allows your little spins to live in this XY plane, then this inner product, let me just call it Y for to be maybe I should call it IJ, not to confuse with the XY. Actually will look like this. Okay, so if theta is the angle to the x-axis, and then basically you got a different model. And this model, as I mentioned, is an XY model, and it has a special U1 symmetry, which means you are allowed to rotate all the spin with the same angle phi, and then this Hamiltonian is invariant, and it is obvious to see because if theta I is replaced by theta I plus phi, this cosine value is not going to change because we care about the difference of theta, so this phi will eventually be cancelled. But why we talk about that? Because I probably will not have time to talk about it, but maybe in statistical mechanics 2, I will talk about it. The fact is, in 2 dimensions, it turns out this model, the XY model, cannot have a true long range order. What do we mean by that? Roughly, it means that if we, naively think maybe we can have a order like all the spins pointing in 45 degrees direction in 2 dimensions, it turns out this picture is not right, because something strange is going to happen and kill this particular order. And that actually connects to the 2016 Nobel Prize. There's something called KT transition, or also known as Kosterless-Thouless transition. I'm not quite sure whether I can spell it right, but I'll try. Kosterless-Thouless transition. And there are something related to topology and things like that, but I think I'll get too distracted if I continue along this line. But anyway, there are interesting questions there, and if you are in you want to understand more, it will be a very interesting subject to explore. Okay, but anyway, we just use this 2-dimensional Ising model and consider the effect of entropy at non-zero temperature. And what we found is that there's always a critical temperature such that the order is robust and it is not going to be destroyed for the Ising model. And if we try to summarize what we have did for finite temperature, let's try to do that. This is 2D Ising. Let's see, what should I do? I should make a bigger figure. Okay, so now I'm going to plot a three-dimensional phase diagram. It might require some imagination about what that is, but I think it should be doable. Okay, so the three coordinates are, one is the temperature, and the other is the external field, and M is the magnetization of our system. Okay, so at t equal to 0, basically we are sitting at this MB plane, and as we mentioned, we basically have a rough idea that the phase diagram should look like something like this. When B is positive, we should have a non-zero magnetization, and we don't know what happened at B equal to 0 at this moment, but I will describe that a little bit later. But when B is negative, basically the magnetization will be -1. So that's what we know at zero temperature limit. Okay, so we ask what happened at finite temperature, and the argument of this domain wall structure tells us that yes, there will be a regime where this order will be more or less survived and will not be completely destroyed by this fluctuation of the domain wall. But the fluctuation is still there, so we anticipate, if we think about what happened at finite temperature. Let's try to shift it somewhere here. Let me. Okay. So now we are trying to think about the finite temperature region. Again, at zero temperature, we don't know what happened, but I'll just try to make draw a picture to guide our eyes. Okay. So now we are trying to go to the cut with finite temperature. So to some extent, right now, because the thermal fluctuation kicks in, so we expect, if we are at some, we add a little magnetic field such that we prefer to align our spin along the positive direction. But because of the finite temperature fluctuation effect, we actually expect our magnetization to be smaller. And we can ask what happens if we try to increase the magnetic field. So to some extent, when magnetic field is stronger, that means that we prefer those configurations with more spins pointing in the positive direction. So it means that the magnetization should increase. So we are anticipating something like that, saturating to the value of 1. So if we make a very, normal extension to the approaching to the zero magnetic field limit, we will anticipate a curve that looks like this. And in the opposite magnetic field limit, we also have a similar behavior that we expect it to have things like that. And their curve is just because my hands is shaky, but you probably get the idea that they will saturate at the -1 magnetization. Okay, so what this figure tells us is that there should be a temperature below this temperature. We still have more or less the correct magnetization, but once we are over this critical temperature Tc, then the magnetization should went back to 0, because now when temperature is high enough, we are still happy to create more domain walls to destroy the order pattern. So at some point of the Tc, the magnetization will become 0. And to some extent, that's something that we know for sure. And above Tc, no matter what kind of BFO you add, when the temperature is high enough, you know that here are all the paramagnetic phase, which means all the spins are disordered. Okay, so right now it is very tempting to just draw a line to continue this pattern. So in principle, it should look like something like this. And you will anticipate there will be some kind of something like this. So you can roughly imagine what the phase diagram should look like. It looks like some kind of a surface. I have an open some kind of like branch cut nearby the magnetic field B equal to 0, and there's just some kind of curve. I'm not quite sure whether that will be helpful, but I'll just draw it. Maybe not. Let me try to do it another way. Oops. So the curve should look like this. Or the surface should look like this. Okay, and after that, everybody is like a plane surface. Okay, so we roughly guessed what is happening, as we also mentioned a little bit during the question. When you are going from the high temperature limit at exactly B equal to 0, you will hit this point where you need to choose whether you are going to follow the plane toward the positive magnetization direction, or you are going to follow this plane to the negative magnetization curve. And this point is when spontaneous symmetry breaking happens. Okay, so through several physical arguments, we can more or less understand the heuristic meaning of the phase diagram. So in principle, we don't need to do any sophisticated calculation to get this idea. So now we are going to discuss this spontaneous symmetry breaking idea, which is like the crucial part of today's lecture. Okay, so let me try to write down the Ising model again so that we know what we are talking about. Okay, and here we assume J is smaller than 0, which is the ferromagnetic coupling. So the first thing is that Hamiltonian usually is like energy, which means it is a singlet under symmetry transformation. And it just means invariant under symmetry because it is just a pure number. And the second question is that because we want to discuss what is the symmetry of the Hamiltonian, we need to be specific about the rules. So usually when we talk about the symmetry, we are talking about a operation that acts on the dynamical degrees of freedom. So what does that mean? It means that in this Ising model, the dynamic degrees of freedom is basically the spin operator SI. So usually when we talk about symmetry, we consider the coupling J and the external field B to be parameters. Sorry. Okay, so that's the rule of the game. So we can try to ask, excuse me, maybe I'll get a cup of water. Okay, so there are several symmetries. One is the Z2 symmetry. Which means that you just flip all the spins. Another important symmetry for the system is the sublattice symmetry. Which means that you can color your lattice by two different colors that are not forming nearest neighbor pairs. So you can always have the color scheduled like this. Okay. So we'll try to first explore the effect of Z2 symmetry. So if the magnetic field is 0, then obviously flipping all the spins, the Hamiltonian is not changed. So we said when so we said the system has Z2 symmetry when the external field is 0. So on the other hand, if the external field is not 0, we will have a term that looks like this. And after you flip the spin, it will look like this, which is not equal to the original expression. So we said the external field breaks the Z2 symmetry explicitly. Okay. So at this moment, I want to emphasize that we did not discuss the microscopic origin of the spin operator Si. Right now, we just assume that it is +1 and -1. But sometimes, if we say the physical model that we are using is trying to describe a magnetic system, then we have specifically attached this binary variable with magnetic moment. Then, as we know, if we consider this spin as some little magnetic moment, which means that there are some microscopic current that generate this magnetic moment. So if we are able to perform a time reversal operation, which is, of course, we cannot do that to a material, but if we can do that, then this spin operator will flip a sign. Okay, but it is also possible that we try to use this binary variable to describe a electric dipole moment. So in this case, basically when you reverse the time, the spin operator is not going to change, because now it is not related to current, it is related to the static distribution of the electric charge. So I just want to say that what is the microscopic interpretation of the binary variable actually could depends on the system that you are describing, but most of the time we'll just use Z2 symmetry to describe our system, because of the behavior that no matter what kind of physical operation, as long as you flip the sign of your spin, the Hamiltonian is basically not changed. If it is the case, then we said that the system has a Z2 symmetry. Okay, but there's another interesting connection, or an interesting side remark. As we mentioned, the magnetic field coupled with our little magnets through the external field B. So if this little spin is really a magnetic moment, and this B is really the external magnetic field, then we can ask what happened if we perform the time reversal symmetry. Okay. Oops. So why do I discuss that? Because it is actually quite confusing. So let me try to elaborate more. So this little SI, to some extent, is describing the little moments inside the material. And this B, which is external magnetic field, usually it is created by some kind of wires or coil that you set up in your lab. Okay, and for this current direction, effectively you will generate some magnetic field pointing in the Z direction. Whenever we talk about the time reversal symmetry, usually we are not allowed to, as I mentioned, reverse the time in this material. However, we are allowed to reverse the time by reverse the direction of the current in the coil. So what do I mean by that is we can do that. And by doing so, the magnetic field is pointing downwards. So that's in reality, but if we think about the thought experiment that we So let me put it in this way. So in reality, we can only control the current flow of the coil. There's no control over the current flow inside the material. So to some extent, when we perform the time reversal operation, we are doing the time reversal operation in a separate fashion. That inside the material, we basically did not touch it, and outside the material, we use the current flow to change the direction of the magnetic field. But we can still think about the thought experiment that if we are able to literally reverse the time globally, that is, we reverse the current inside the material and also the current of the coil, the effect is our little spin will be flipped, but also the magnetic field B will be flipped. And if that is performed, then we will realize that the Hamiltonian is invariant, even when magnetic field is non-zero. Okay, so let's try to use this thought experiment and try to construct if this operation will lead to the same Hamiltonian, what it will lead to for our partition function. So basically the partition function let me try to be more specific. Suppose I have some partition function that is written like this. Basically, I sum over the Boltzmann factors for this configuration, where we start with the magnetic field pointing in the direction of minus B, and we sum over all the microscopic spin configurations. And because we notice that if we think about the summation, it actually sums over all the spin pointing upwards and all the spins pointing downwards. So to some extent, I can think of this summation as the summation but with all the spins flipped. And the reason I can put a minus sign here is because I don't care what is the order of my summation. I only care about the total sum and the operation of addition and basically commutes. So now we are going to use the trick when all the spins are flipped and when all the magnetic field is flipped, they will correspond to the same Hamiltonian. Okay, and that will be the partition function of our system with the opposite external field direction. Okay, so if it is true, then we will get a conclusion that the free energy of our system should be equal to the free energy of our system with the negative, it should be with the opposite direction of the external field. And then we can try to calculate what is the total magnetization by this formula. Here, this M is the magnetization density at the finite field B. And here's the number of spins in our system. By definition, it should be related to the free energy, taking derivative with respect to the field. And as we mentioned, that this free energy is equal to the free energy with the opposite field direction, and we can absorb this minus sign into the denominator. And this formal expression is actually the magnetization evaluated at the magnetic field minus B with a minus sign here. Okay, so now we have this seems like a very nice equality, and eventually this leads to the fact that m omega b is equal to m omega of minus b. So this relation is kind of a disaster because it tells us that when B goes to 0, the magnetization must be 0. Or maybe let me try to write more explicitly. Because of this relation. So I just give you a question to think about, because just several minutes ago, I told you that when the B field is 0, when the temperature is lower, the system will have some spontaneous symmetry breaking, which means that the system will choose side. Either you will prefer to have magnetization to be positive or magnetization to be negative. But now I'm telling you that from the symmetry of the system, which has a Z2 symmetry, and we also notice that if we do a thought experiment, when we flip the direction of the magnetic field and the spins at the same time, and we calculate the partition function, it has specific property such that we know the free energy will look like this, which means the free energy at two different opposite direction of the magnetic field for the Ising model actually is identical. And if that is true, then there's a problem, because we can derive a restriction about the possible magnetization, or the relation between the possible magnetization at opposite direction of the magnetic field. And at the limit where magnetic field approaches 0, this relation strongly suggests that the magnetization must be 0. How is it possible that we eventually have the spontaneous symmetry breaking. So that's the point why something is strange is happening, and that is related to the fact that thermodynamic limit needs to be taken care of seriously. And the reason that thermodynamic limit needs to be taken seriously is because at the step we go from this line to this line, where we go from the free energy expression to be the same at positive B and minus B. And we said that what we are doing is just formal operation, and these two expressions should be identical. It is true if this free energy F is differentiable at this magnetic field B. So if the free energy is not differentiable at this magnetic field B, then this equality might not hold. And it turns out it is what happened at the spontaneous symmetry breaking case. And the quick idea is that let me try to draw the figure very quickly, and then we will end our lecture today here. Sorry. So for finite system, this free energy actually is well-defined smooth function, as we just discussed, because we sum over a finite number of terms, which is just some exponential function, so it must be smooth also. However, at thermodynamic limit, when you sum over infinite many of them, there's a chance that you actually have something that looks like this. So indeed, this free energy is a continuous function at all the magnetic field, but at B equal to 0, it is actually not a smooth function. So it is not really differentiable. So when you evaluate the magnetization for a finite system, you might find something like this. And let me assume it is finite. You'll see your magnetization will be 0, but whenever you are at the thermodynamic limit where n is large, it allows you to have a sudden jump of your magnetization when the magnetic field is 0. So the spontaneous magnetization actually need to be calculated more carefully. Naively, we think we should perform this differentiation if this FB is well behaved. But if it is under that situation, then we will see this implies when the sorry, this is not H, this is B. When the B field is approaching from the other direction, this differentiation will have a additional minus sign. So if I try to decipher this expression a little bit further, what it means is that we are taking the limit of the magnetization by first, actually we want to take the system size to infinite, which means it is the thermodynamic limit first, then we will take the external field goes to 0 limit later. If you calculate that, you'll see this magnetization is non-zero, but if you reverse the order, this thing will be 0. So this behavior is suggesting that there are some non-trivial behavior at the thermodynamic limit, which is a hint that spontaneous symmetry breaking is actually an emergent phenomenon. That actually you need to go to the thermodynamic limit to really see it. And it also suggests that the non-trivial analytic relation, whether you take the thermodynamic limit first or you take the external field that break the symmetry first, actually matters. And that's the first discussion about what do we mean by spontaneous symmetry breaking and why thermodynamic limit is actually very important. So you might have a question like, how come I know I should anticipate this type of behavior instead of the smooth free energy behavior? We'll justify that a little bit later by using the 1D Ising model. But I will also justify another thing, which is at this moment we are trying to rely on the mathematical understanding, which is the analytic property of the free energy. But actually there's a more statistical mechanics point of view to understand why thermodynamic limit is actually quite important to see this kind of spontaneous symmetry breaking phenomenon. And sorry for going over time for 10 minutes. I'll stop right here. And if you have any question, you can unmute yourself and ask me. Thank you.